We already know that we can use the first derivative test to find the local maximum and minimum. In this video, we will see that we can also determine the local maximum and minimum by using the second derivative test. Okay, so what is the second derivative test? Let's first look at the definition. If the second derivative is less than 0 on an open interval from a to b, and if the first derivative is equal to 0 at the point x equals c, where c is between a and b, then the function fx has a local maximum at the point x equals c. And if the second derivative is positive on the open interval from a to b, and if the first derivative equals 0 at x equals c, then the function has a local minimum at c. Okay, so why does the second derivative make sense? Why does the second derivative test tell us the local maximum, where the local maximum and the minimum is? Let me use this graph to explain this to you. Okay, now here we have a open interval from a to b. Because we know that the second derivative is negative. Therefore, according to what we have learned, we know that the function gonna be concave down. So it's gonna be like this. Okay. Now, then there is a point x equals c between a and b. Let's see, c is here. Okay, so the second derivative at c is also negative, right? Because it says all the second derivatives are negative any points from a to b. And because the first derivative is 0 when x equals c, so we know that at this point, we must have a horizontal tangent line. So at this point, f of c, the function has a local maximum. Okay. Now, in another case, if the second derivatives are positive between a and b, so the function gonna be concave up. And at c, since the first derivative equals 0, so the function gonna have a local minimum. Okay. Now, what if the first derivative and the second derivative, they are both equal to 0 at c? If this happens, then we are not able to use the second derivative. Let me show you why. So, for example, let's consider 3 different functions. One is fx equals x to the fourth, and we let c be 0. And then the second function will let be x equals negative x to the fourth, and c still be 0. And the third function fx equals x to the third and c equals 0. All right. So for the first function, its first derivative is 4 times x to the third, and the second derivative is 12x squared. And when x equals 0, the first derivative is 0, and the second derivative is also 0. Now let's take a look at the second function. For the second function, the first derivative is negative 4x to the third, and the second derivative is negative 12x squared. And when x equals 0, its first derivative and the second derivative are both 0. For the last function, the first derivative is 3x squared, and the second derivative is 6x. And when x is 0, this is a 30 squared, and the second derivative is 60. Okay, now we can see for these three different functions, when c is 0, both the first derivative and the second derivative are 0. However, we're gonna see we have three different results. Okay, when for the first function at 0, the function has a local minimum, right? For the second function at 0, the function has a local maximum. For the last function, at x equals 0, the function doesn't have neither maximum nor minimum. So from this example, we can see that when the first derivative and the second derivative are both equal to 0, we may have three situations, and those three situations are the function could have a maximum, or could have a minimum, or the function doesn't have neither maximum or minimum at c. Now, in this case, what can we do? If this happens, if the second derivative couldn't tell us any information, we need to go back to use the first derivative test.